Good morning. Before I introduce my group members and my project, I'd just like to play a quick video. Thank you. My name is Taylor Skilling. I'd like to introduce my group members. We have Will Johnson, Chris Kenyon, Nick Tosta, and Brandon Wynn. And we're here to talk to you today about localized air pollution monitoring with AirMap under our advisor, Professor Shah. So today we're going to talk to you a little bit about the design problem, why we came up with this solution, the potential solution and our design for it, the conceptualized and realized solution, what we actually came up with before presenting you with some results, and finally concluding with questions. So the motivation behind this project. Air pollution is a silent and invisible killer that affects millions of people around the world. It increases the risk for health disease like cardiovascular, respiratory diseases like asthma and chronic bronchitis. It increases the risk of cancer, and also it increases the risk of adverse birth defects. It also presents an environmental impact. You can see here in this picture of the Shenandoah National Park in Virginia, versus a clear day, versus a day clouded by haze coming from the fine particles produced in that region due to the production and burning of fossil fuels. So to get some research and a little bit better understanding of this air pollution, we conducted an investigation and met with two industry and academic professionals. So you can see on the left here, there's Dr. Helen Suh. She's a professor at Northeastern and also at Harvard. And she's really motivated in interdisciplinary understanding of air pollution. So she goes out and collects data and also predicts what kind of air pollutants might be present in a given region. So we consulted with her, and her general sentiment was that there is definitely a need for a better air pollution monitor. She also introduced us to David Sittenfeld, who works at the Museum of Science. He's somewhat of a citizen scientist. That is, he goes out and collects data and uses that to inform policymakers. So he has a really good idea of what kind of devices are out there because he's actually gone out and collected data with them. His sentiment as well was that if we created a project that met his needs, he would absolutely use one.
As part of our research during Capstone 1 over the summer, we did a teardown of some competitive devices in the market. The TSOA, the AirBeam, the Air Quality Egg, as well as a product that's no longer on the market. So this was a complete teardown, including what technologies they were using for communication, what sensing capabilities they had, and what data visualization they had down their information pipeline. We found that there really was a need. There really wasn't a device out there that satisfied the needs of our customers. And it was also a great jumping off point for the mechanical and electrical design.
On top of that, we realized that with these systems, there's no good visualization platform. So the average user wouldn't be able to easily see how air pollution actually exists in the locations around us. So you see the EPA is one of the biggest providers of sensors in the United States. And this is about how granular their data is. So if you go on airnow.gov, you can only see at pretty much a county level. And if you look at New England, I mean, most of it doesn't tell you any data. So that's obviously a huge problem. I think there's only about 14 sensors in all of Massachusetts. So you want to see, and those are all at fixed locations too. So you can't even move those to see how air pollution data might look in more local environments. So that was one of the big requirements that we see, or big motivations that we saw for making this product.
Yeah, so our system requirements moving forward was a portable and discrete product that was real-time, low cost, and easy to use so we could hit both researchers and consumers. We also, through our research summer 2, decided to use particulate matter and ozone because these are chief irritants for air pollution impacting human health. We also, on the data visualization side, needed a system that was likewise easy to use. We wanted that data to be accessible, but we also wanted to use the data as a platform and aggregate all the data in a way that would help people to see the broad range of data and to see the animations and to be able to use other people's data to impact their life and make decisions. Now I'm passing it off to Nick for the conceptual solution.
So, how do we solve this problem? The solution is the AirMap system. There are three main components. The first is the AirMap devices. These can be purchased by consumers for personal use in their neighborhood, in their home environments, or by researchers, even municipalities, to collect a broader range of data over a larger area. These devices could be placed in fixed locations or given to something like a mail carrier or perhaps even the duck boats. These would act as a force multiplier to gather data around the city with a single device. These AirMap devices would then transmit their data over a cellular network to the AirCloud server, which aggregates and processes the data and then serves it to our web interface so that anyone that's interested in our data can access it and view the pollution situation where they care about it most. The hardware concept begins with our MCU, which we've chosen a Raspberry Pi for its ease of use and rapid bring up. That controls our GPS and cellular module for geolocation and communications. It also controls our display for real-time feedback, as well as the fan, which brings air into the system and over our sensors, which we've chosen a PM 2.5 and ozone sensor, as those are the primary irritants, as well as a temperature, humidity, and altitude sensor for drone-based applications. And then, of course, the system is rounded out by signal conditioning, power, and a battery charging circuit.
So looking at our software solution, it's designed to support a unidirectional flow of data from the device eventually to a web front end where you can view the data easily. So on the device, we have code running that will collect data from the sensors, store it locally, and then every 10 seconds we'll send to our cloud server with a GET request containing its most recent data. The web backend is implemented using a Python Django framework with a MongoDB integration. It's responsible for storing data from the devices, processing it, analyzing it, and then eventually serving up web pages to a client-side visualization. In the web front end, there's a map where you can visualize where pollution is good or bad, and then you can query backend for more data to animate it over time, or even view live data as it comes in. So we're going to take a quick look at the actualization of what we realized. Here's a picture of Nick, who's using both the website here, where you can visualize data, and the device that we packaged that will collect data.
Yeah, so how do we actually put all this together? We started out with a rapid design using a breadboard, so running through iterations of the electrical design, seeing what really worked, using breadboards where we could, or breakout boards where we could, to facilitate the design process. And then once we had locked down the electrical design and done some initial characterization, we went over to a non-enclosure device, which is essentially the electrical design without the mechanical constraints. Then, to satisfy those mechanical constraints of portability and discrete packaging, we designed our own PCB. So, some things to note here, we had some unique cutouts to really satisfy that portable design and to facilitate airflow. We also separated the noise and measurement stages, or the especially noisy stages such as power conditioning, and the measurement stages like the high precision ADC that we were using on the PCB, and stuffed it all ourselves.
So, a lot of our constraints are, to satisfy a tight, well-integrated device. It's easy to use, portable, and in order to satisfy those requirements, our team custom designed and built our own mechanical enclosure. As you can see, we've spent a lot of attention to detail in every aspect of the design, including modeling all of the screws and all of the connectors to ensure ease of assembly. Another interesting detail that came up is it turns out that material selection was critical. Many common materials such as plastics and even aluminum can absorb ozone and later release it or break it down or be broken down altogether. So these obviously would impact our sensor readings. Polycarbonate was chosen because it's a relatively inert material while still having the mechanical properties that we would want for such a device. We also paid a lot of attention to airflow through the device. So as you can see here, air enters through the front of the device, through the PM2.5 sensor, and then passes over the ozone and under the temperature and humidity sensors before being blown out the back of the device by a fan. This single direction airflow greatly reduces the sensing time and improves the consistency of our readings.
So to communicate with these different kinds of sensors, we wrote various types of code, including C, Python, and using the AT interface. You can also see here that we have some data switches. This allows the user to really tailor this device to their experience, whether they're going to be using it in real time. You can control whether display is on and off to save battery power. If you're going to be using this in a remote location where it needs to last a lot longer. I'd also just like to emphasize here that we use the Raspberry Pi, which runs the Linux operating system. So for a sensor like the particle sensor, which requires really strict timing, we actually got down to the register level of the Raspberry Pi in C and made sure that we could consistently get an accurate reading.
So this is a quick look at the website itself. We wanted an intuitive, easy-to-use UI where you could query data and have a clear representation of how it looked. So if you look up at the top, there's selectors for the different type of particles that would indicate different pollutions between ozone and PM2.5. So you specify a time range for the data. You can enter a location by querying, which will leverage Google's location search API. You can also search by coordinates or by zooming on the map to where you'd like to search. You can select the type of data, whether it's EPA data, which we've backfilled by pulling from their site, or air device data. You can also register certain devices to a user account so that you know it's your device. And then if you look here, there's 3 buttons. Submit will give you just one snapshot over time, and the way it's going to show up on the map is different colors that will overlay on top of the map by location, with green indicating, healthy air pollution levels and red being bad. Animate will allow you to look at how something's progressed over time, and will show you where your sensors were over time and how the pollution levels have changed. And then live is a live visualization of incoming data.
So now we're just going to step through a quick demonstration of how a user who just bought the device might use it. So let's just step through this here. So a user will get a device, and it'll come with a device ID on it. So first they'll come to the site, they'll register it. This user, I speculate, is a very good-looking guy. So he's gonna put in his name. He's gonna create his user. He's gonna contact us. Oh wow, how nice. He's gonna contact us for an API key. We're gonna give him an API key, and then we'll be in touch with him too, and we can see, we'll have him. Then he can start adding his devices to his username. Once he does that, he can go back to the home page and he can start using this system. So like we said, we have 3 different methods. The first method is this live animation. So we can see we have this sensor on Northeastern's campus. So you can see he's getting a green indicator all at once, and you would see anyone's device data coming in live as well if there were other users. You can also animate his data. So this is a walk that we did the other day, walking around campus. You can see right now it's all green because we live on a green campus and everything's going to be healthy, so you guys are breathing fine, don't worry. On top of this, we can also, so the concept is that this is an evolving platform, so it would eventually have a lot of data. So this is an idea of what it might look like if there were a lot of users along the city. We can see like maybe towards the Pike it would be a little worse air pollution. So you can also animate that and see how that would change throughout the day. So maybe an expecting mother wouldn't want to go out to an area like the Pike at a certain time of the day if it were more polluted. So we can also export any of this data. So if this were a researcher that wanted to do further analysis of this, then they can come down here, they can scroll down, and they can get a CSV file. And then you can do whatever sort of analysis you want in Excel or however you choose to. And on top of that, we've supplemented this data with data backlog all the way to 1980 from EPA data. So on top of this, we can submit queries for EPA data. We can select any one of these markers. These are all fixed locations. And we can get a historical chart of the moving average of data, or of air pollution data over time. You can also export that and compare it to your other air data that you've already accumulated.
Thank you, Chris. So So just in summary, Chris went over the 3 different ways that you can look at our data. You can get a live look, you can animate over time and submit a simple query, and you can also see our device pictured in the bottom right, which will give you a live update as you're walking around, as Brandon mentioned, every 10 seconds. So as we've demonstrated, there's a lot of data that comes out of this device, and how are you supposed to make any sense of it? You can see here on the right an example database. This is a single, an example database query. This is a single sample that we get. You can imagine that's multiplied over multiple users and also varies over time. So you can use a technique called principal component analysis, which will distill this matrix down and really reveal what factors influence most the highest concentrations of pollutants, So you could see whether maybe the location or whether it's the time of day or time of month really makes the biggest factor in a high concentration of air pollutant. A simple cost analysis here. If you recall from the previous slide, some of the devices that we were looking at were around $600 per se. We presented this device at around $260, which is a very competitive price, and also provides a much richer and more impactful data visualization and device experience. Also, there should be noted that this device was basically a one-off, or multiple were made. If we were to produce this at scale, of course, the highest cost of the printed circuit board would go down, and this would be even a more competitive price point. So in conclusion, over the past 6 months, we've researched a novel and impactful problem, researched the best way to do it, came up with a feasible plan that we thought we could accomplish over the 6 months, and actually did it. So I'd just like to really thank my group members and our advisor, Professor Shafai, and all those out there that helped us with this project. We'll open it up to any questions, but thank you very much.
Are these devices being used? And I guess that would be the first question. And the second is that, having this massive amount of data and then being able to take that data and other factors to be able to predict pollution models and that sort of thing would seem to be a great application. You had any discussions or thoughts on that?
So, yeah, so for the first part, there's really no existing data. That's kind of the issue is, there's EPA data that's very reliable, but as we mentioned, there's only 14 monitoring stations in all of Massachusetts. So because pollution is so localized, that data really isn't super impactful. As for existing devices, like I said, there are some citizen scientists and some researchers conducting data with expensive laboratory-grade equipment, but that's only suitable for small collection runs. They can't be deployed at scale. And then the devices that can be deployed at scale simply don't collect enough data and aren't geolocated. So there's really just no existing solution. Would you like to take the second part?
Sure, I can speak to the data. Yeah, so, we only have a couple prototype devices right now, so we haven't generated a ton of data right now, but that's why we looked into the principal component analysis, because we predict that with methods like that, we could start to get trends out of massive amounts of data that we could accumulate. So, it's an idea right now. We don't have the data to back it, but we would hope to be able to make those impactful conclusions based on that.
Does that answer your question?
Yes, thank you.
Great job, guys. A question is, so these units are probably going to be, if it goes into production, or if you use a few of them, they're probably going to be used over a long period of time. Have you given any thought to how you can ensure that you're getting accurate sensor data over a period of time? You're passing air over your sensors, and I can't come to that.
Yeah, that was one of the concerns, and even sensor reliability over a long period of time. One of these sensors that we selected has a 10-year estimated lifetime. One of the things that's missing from the mechanical design is a filter over one of the sensors. These are things that need to be added in production, of course.
Mechanical.
Yeah, a filter for the ozone sensor. So these additional considerations would greatly improve device lifetime. Yeah, we estimate that they may need periodic cleaning, especially in highly polluted environments. They probably would need to be cleaned every few months. I believe that's what the EPA devices do, is they get cleaned about every 6 months. Fortunately, most of the devices, one of the recommended ways to use the device is on a mobile, something that moves like the duck boats or like a drone. So those, of course, if they go back to a base station every night, that would be convenient for cleaning and maintenance.
So I'm curious what you found in the way of deficiencies in hardware design when you tore apart the prior devices, or what improvements you felt were the biggest strides forward that you wanted to achieve.
Yeah. So first of all, it was really a lack of, like the devices themselves didn't have the capabilities to begin with. They lacked geolocation, relying on the geolocation from your phone, or they only sensed PM 2.5 in most cases, so there was no gaseous readings at all. But we also found that the ozone sensors prior to the sensor we're using is actually was out in 2016 and is pretty new. It uses an electrochemical process that doesn't heat up the device, which obviously would alter readings. Old devices required a heating time, which had a turn-on delay at the beginning, and would alter the readings by heating up the device.
Great projects. Airflow is such an important parameter in this project. More importantly, how to control airflow, right? So my question is, on the fan control side of things, how did you determine, or how did you settle the specific fan and the specific air speed, of the fan?
So these problems were solved mainly by looking at the characteristics of the PM sensor. So the PM sensor, actually, I believe it had a recommended airflow through the device, and then we selected a fan with a size and sized the holes in the case to approximate those parameters.
What was the reaction of your original research consultants? You said that one of them would use your device if you built it more.
Yeah. So they were both very excited that there was someone looking into this. As I mentioned before, the Professor Helen Sook, she is an interdisciplinary member, and so she's worked and collected data before, and each time she had to get a graduate student to go and buy an Arduino, buy sensors from it, write code, and that code only works specifically for her application. So if she could have a device that she could take around and do multiple data collections with for whatever project she was working on, that was really the goal for her, was not have to rely on a very expensive but very accurate sensor, or a not as reliable sensor that her graduate student made that could be only used for a one-off project. She really wanted that all-encompassing solution, and that's what we strive to provide her with. And same with David, is he had gone on these data collects before and was frustrated with the devices that were out there and was wanting to keep conducting his studies and really needed a better device. So if we could provide him with that device, like I said, he really wanted to use it.
So did he think you did?
To be determined. We wanted to present this before we showed
we
it.
provided him some status updates, but we actually haven't, the full enclosure device, we've only just put together recently and just started collecting data. So we're really excited to show him the data that we've collected. We think he's going to love it.
Just a couple of days ago, we finished.
So then we also have
That also you can go out to see the device actually that they made.